core index that's running it, for what it's worth, and some data token. And it can either panic, fault, track, stop, like, this isn't good, or it can output some data. If it outputs data, it means that the authorization is okay. It gets to choose what data it outputs. The combination of the function f, the hash actually of that and the para, those two things hashed together give you the commitment that has to be in the authorizable. So you basically say, I want this function to the thing that that authorizes the work that I want done, and it should be parameterized in this way, and then you hash all of that, and that's what you put in the pool. That's how JAM knows how to recognize the right work to be doing on the core. When authorizers run, they can't just use arbitrary amounts of gas. That would be a potential spam attack, right? So they're quite limited in terms of the amount of computational steps that they can do in order to get to a conclusion of either data or tracking. And then any data is fed into the refine stage, and actually into the accumulate stage as well. Okay, this seems like a pretty sophisticated system. It's like, what's the end game here? Because I gave you this like picture with just the arrows going down. JAM doesn't look like that. So what, that's the ideal thing that we want. How are we going to get there if all we have is this like sophisticated system? Doesn't look like that. Well, the answer to that is CorePlate. CorePlate is the service that we want to make on JAM beyond a service that's compatible with Protocol. To understand what CorePlate is solving, we have to sort of rewind a little bit back to the previous stuff that I was saying about partitioning. Why do we have more chains or more L2s? Well, we want to scale out. It's not so much about specialization or sovereignty, it's really about scaling out. What's the problem with using lots of chains to scale out? Fragmentation, right? Persistent state partitioning, the fragmentation of state space. Why is fragmentation such a big problem? It limits network effects between the different portions of the system. It limits the use cases, limits atomicity, limits developability. If you're a developer, it's actually hard to develop an application over multiple state spaces, like very hard. And as a team who is looking to deploy somewhere in this map blockchain world, it kind of forces you having to decide where to deploy without really knowing how things are going to be like in the after deployment. Once you're deployed into a particular L2, particular ecosystem, it's really hard to move away because state is partitioned. Right? Those walls are thick. And that's not so good. We don't want walled garden. A big playground. So let's go back to the thing. This is what we're after, right? This is what I was sort of saying was what we want. Just lots of different state machines, all doing their thing, running concurrently, and interacting where they need. That's JAM. That doesn't look like that. See, they're different. This is quite complex. But JAM, as I said, is really the sort of the launch pad. This is CorePlate. This is the computational model of CorePlate. Now, we can't do this properly. This is physically impossible. Yeah, like physics prevents us from doing this, making it scale to the degree that we would want. So we have to have some sort of management of this coherence, right? We cannot have full coherence. We have to manage the decoherence in some way. But we want to manage it in a way that doesn't impact too deeply on our ability to have atomicity, our ability to develop well, our ability to deploy and not worry too much about maybe wanting to move around somewhere in the future, our ability to have good network effects. How do we do that? Well, I mean, the solution is relatively simple when you look at it. We have agile state partition, not persistent state partition. We partition the state as it needs to be partitioned, as it's economically sensible to partition at any given time. You can think of core play as essentially a smart contract operating system of JAM. Yeah? It provides a platform on top of JAM for smart contracts. They're actually better than smart contracts. Core play allows for actor-based smart contracts. Wow. Now one thing you're going to notice here is that unlike these other systems, these arrows are not distributed. These arrows go all the way from the top down to the bottom. What does that mean? It means that we have actual Turing completeness. Right? It means that we don't have this per block, close everything down, forget everything, go back, new slate, start computation again, that we have with regular smart contract platforms. We have actual Turing completeness. How do we manage this? Well, we essentially provide a platform, an execution environment, where the software running on it doesn't know about blocks, doesn't know about transaction sizes or anything like this. We provide an execution environment that is really just similar to what you would get with an active system. We still, because everything is operating conceptually in the same state space, allow for the possibility of global elasticity, the possibility of having atomic interactions between any two portions, with any two items within the state space. Essentially, we allow for the possibility of synchronous composition, and yet still provide Turing completeness. It's built on JAM, and therefore it's designed to be elastically scalable across JAM's cores. It can use as many cores as is needed. As you add more actors to the system, it uses more cores. It's elastically scalable. It scales out, not. And it enjoys no persistent state partitioning, so we don't get this fragmentation, either network fragmentation, L2 fragmentation. This isn't a thing. So how do we manage this? This seems like how do you get your needs again? Well, firstly, we use JAM, right? So we have this distributed decentralized data lake. That's where the actor's state is stored. It's available across the JAM, so we can actually don't have to worry too much about storing any particular actor in any particular place, like we would on a system like Ethereum with L2s or where we have to store an actor or a smart contract in a particular parachain. Don't do that with JAM. They all have access to the same data lake. Just stick it in the data lake. With JAM, we have pipelining. This allows us to speed a lot of things up. We should use all of these different cores at the same time. And with JAM, we have PVM. PVM is crucial. PVM is what allows us to have this apparently continuous execution mode, like this actually Turing complete execution mode. We distribute our state into much smaller pieces than a blockchain system. Polkadot, for example, distributes its state, its overall state of Polkadot, into quite large pieces. We call these pieces parachains. It makes them quite hard to bring together. Because to bring together two parachains, you have to have a system that knows everything about both. And then it picks and proves the bits of state that it needs, so it does that together. It also means that unless you have a really good way of ensuring that that there is no collisions between the bits of state that you're using and changing, it means there's no way of having two different sets of the same parachain have two transitions at the same time. And this becomes hard because your state is sort of already built together in one coherent system. It's really hard to relax that to two independent transitions. I'll go into why I'm sort of diving into that a little bit later. But by arranging state into smaller pieces, smart contracts, actors, it allows for easy composability, like essentially co-scheduling, easy access. We also regularly space once every 6 seconds, maybe even more frequently than that, but at least every 6 seconds. As is needed. It may be if the partition is economically efficient, then we end up not rearranging at all. But it costs us enough. It costs us a minimum amount to repartition. Yeah, I'm not going to go too into this. These are sort of other ways of doing it. One of the other ways of sort of trying to get something like this would be to work not at the level of smaller state machines, but at the level of like whole L2s, like whole rows, whole parachains, and just try and co-sequence them. Right? So basically having these giant machines that track both chains, manage 2 transactions, all one, and then try to causally entangle transactions across them. Now, this has a lot of problems with it. Theoretically, it's like you can do it, but you will end up with, ultimately it will be unstable. Right? You might be able to get somewhere with 2 or 3 chains if you can get a lot of validator support. But there is a huge centralization bias for it. Now the big scaling issue here is that suppose we have 2 transactions on different chains that are causally entangled. Maybe it's some sort of autonomous one. Now if we're doing this in a Turing-complete fashion, which is of course what we want, then those 2 transactions have to be kind of paired, right? Either both happen or neither of them. This must necessarily be the case. If only one of them happens, it's a big problem. And if one of them happens and then the other one can happen, but actually something else mutually exclusive happens, which is what we have to assume is a possibility, then we have a big problem. And we have to kind of rewind the other one back. Which means we kind of have to limit finality or limit the effects of any causal transactions until we know for certain all of their counterparts on the various other chains will definitely take effect. Now, this is, as I say, this can maybe be managed for a small number of chains. It becomes very difficult when we bring in lots and lots of chains. Basically because we have an order n squared problem. Every chain has to track every other chain's transition and be certain that all of the other chains are going to do what they think they will, what they say they're going to do, what the implication or the requirements of this particular effect should be, before we actually go ahead and do the effect ourselves. Kind of all have to either all go into the room or no one go into the room, but we can't possibly have people that look like they're going into the room but actually stay outside. That's the problem. So we have to track entanglement, we have to create entangled blocks. Creating entangled blocks across chains is no easy thing either. We have to essentially make sure that our transactions get in at all. Not so easy. And then we also have to track the opportunities for entanglement. And then if we want to have many different sort of producers all doing a co-sequencing, then we have to have a sort of further issue where, in essence, we're trying to make sure that the 2 different producers don't sort of collide in their co-sequencing attempts. Essentially that if we're co-sequencing 5 chains, then we don't get sort of 4 producing blocks, but actually one is part of some other co-sequence set. The effective, the end of the road for this is centralized sequences. Right? The end of the road for this is just having one giant machine that sequences everything. This obviously isn't very likely. There's also intent solvers, but these don't solve the same problem. They can help. They can help to some extent if we want to use linear chains, but they don't solve the same problem. Good. That's the talk. Thanks for your attention. You're a very good audience. No talking at all.